Hi, my name is Drew Mills, and this is Physics 1, Lab 3. The purpose of this lab was to analyze orbital motion using Newton's laws of motion and gravity. In Part 1, I used the trajectory data from a simulated star orbiting a black hole to calculate the net gravitational force on the star, and then estimate the mass of the black hole. In Part 2, I simulated a system with a planet, a moon, and a spaceship and determined an initial velocity that allowed the spaceship to orbit both bodies without crashing. The system being modeled in Part 1 consists of a star orbiting a black hole located at the origin. The star has a mass of 2 times 10 to the 30th kilograms. In the model, we assume that the only force acting on the star is the gravitational force from the black hole, and that the time between trajectory measurements is 1 day or 1 Earth day in seconds. In Part 2, the system includes a planet at the origin, a moon orbiting the planet, and then a spaceship initially positioned just above the moon's surface. The main physics ideas used in this lab are Newton's second law, momentum, and Newton's law of gravity. Newton's second law states that the net force of an object is equal to the rate of change of momentum. Momentum itself is defined as P equals mv, where m is mass and v is velocity. Since a star's motion is caused by gravity by the black hole, we can also describe the force using Newton's law of gravity. By calculating the net force from the change of momentum and equating it to the gravitational force, we can solve for an unknown mass of the black hole. To analyze the star's motion, I first calculated the star's velocity from the position data using the time interval between measurements. From the velocity, I calculated the initial and final momentum vectors for each time step. The change of momentum divided by the time interval gives the net force acting on the star. Using the gravitational force equation, I rearranged the formula to solve for the mass of the black hole. This calculation was performed repeatedly throughout the trajectory data, and the resulting values were averaged to obtain the final estimation. The simulation showed an elliptical orbit around the black hole. Using the force calculations and gravitational equation, the estimated mass of the black hole was approximately 1.29 times 10 to the 34th. This result is pretty consistent with the expected gravitational behavior. The net force acting on the star represents the rate of change of momentum. The parallel component of the force represents the magnitude of momentum, meaning the star speeding up or slowing down. And the perpendicular component shows change in direction of momentum, causing the star's path to curve and form an orbit. This explains how gravitational forces continuously redirect the motion of an orbit. In Part 2, the simulation models gravitational interactions between a planet, a moon, and a spaceship. The moon experiences gravitational forces from both the planet and the spaceship, while the spaceship experiences gravitational forces from both the moon and the planet. Newton's second law is used again to update the velocities and positions of both objects at each time step. By adjusting the spaceship's initial velocity, I was able to produce a trajectory that was influenced by both the moon and the planet. If we want to predict the motion of an entire system more accurately, we would need to include gravitational interactions between all objects in the system, including the star, black hole, planet, moon, and spaceship. However, some interactions would dominate, mostly the gravitational influence of the black hole being much stronger than the effect of the relatively small spaceship. A possible source of error could be the discrete time steps used in the simulation. Additionally, the model assumes that the star is only influenced by the black hole and ignores all other gravitational forces that could exist in a real astronomical system. In conclusion, this lab demonstrates how Newton's law can be used to analyze orbital motion and estimate the mass of massive objects like a black hole. The simulation also shows how gravitational interactions between multiple bodies can produce complex orbital behavior.